And now in continuation of the theme of analyzing traces and making sense out of huge amounts of data we have, George is going to present some exciting new topic on transient analysis and how we can uplevel our understanding with it.
Hi everyone, this is George Hoffman from the Transient Analysis team at Facebook, and I'm going to talk a little bit about the Transient Analysis project and the kind of performance analysis and insights that it can drive, and give a demo of the system in action. I'll spend this video on slides and screencasts, but I'll pause for a second to give you a face to put to the voice, pandemic, beard, and all. Hi there, I'm a real person. I have a face, such as it is. Alright then, so what is Transient Analysis, or TA? TA is a project that's about 3 years old. It grew out of efforts at Facebook to attempt to understand the behavior of our mobile apps in the wild, including their performance and reliability. These are big, complex apps developed by dozens of teams working in parallel, intentionally with minimal centralized architectural leadership. And Facebook relies on a good feedback loop from telemetry and production apps to let us all know how we're doing across the huge audiences we serve. This is true of efforts to improve performance as much as it is for top-line metrics like engagement. But understanding the many causes of performance problems of a complex app in the multitude of real-life scenarios that are encountered in production across billions of users is very challenging. Making this understanding actionable and being able to validate that any action taken has had the intended effect is even harder. Transient analysis is being developed to meet this need to characterize product behavior, including performance, at this huge scale, to discover and understand the often surprising factors and scenarios that drive the movement of performance metrics, or that may be hidden by those top-line numbers, and to provide guidance to engineers going after these problems. In order to get to this level of detailed understanding, TA works with session trace data sourced on mobile devices. These are sets of structured logging events that depict what each of a dozen different layers of code in our apps think is going on at any given time. Transient analysis lays out a methodology for modeling the modules and processes producing this telemetry, expressing the relationships and domain rules between them, deriving meaningful high-level signals, aggregating those signals across millions or billions of sessions, and exploring the categorizations and visualizing real examples of interesting or problematic behaviors. TA is an integrated data engineering system built atop Spark, designed to support this methodology. In practical terms, it consists of a modeling framework for describing, visualizing, and transforming session data, a workbench environment supporting an agile workflow for the development of domain modules enabling quick iteration between aggregate analysis, visualization, coding, and debugging, a pipeline that runs these domain modules against session data at scale, exports to various tool surfaces, and generates metadata on data quality and model drift, a front end that allows model exploration and visualizations in terms of modeled high-level concepts using simple declarative definitions, and a growing library of these domain modules that encapsulate all the domain logic needed to understand a particular domain, to transfer low-level telemetry to high-level characterizations of performance, and to visualize scenarios in terms of these high-level concepts. These components work together to support a performance analysis methodology in the form of a development workflow. First, we join and pull all relevant data for each session from whatever data sources into main memory and process whole sessions at once. This can include mobile source telemetry as well as CDN logs, peer device traces, or other relevant server logs or metadata. To analyze this data, TA provides an environment to write, review, debug, test, commit, and maintain actual code. If you've ever tried to write SQL to interpret and associate multiple streams of structured log events, you know how challenging that can be. We don't use SQL, but do our analysis using a general-purpose language, usually Scala, not any kind of specialized query language. Working in a general-purpose language like Scala that also has great support for a purely functional style lets developers mix pure immutable transforms with any messy imperative logic needed to solve many analysis problems, which are impossible or intractable in SQL. Many TA domain modules use this flexibility to apply heuristics and apply optimization algorithms to fit inevitably dirty data to an idealized functional model in order to judge its conformance to that model. The TA workbench provides an environment for quick iteration on this analysis code, computing and caching partial results in memory, hot loading new analysis code, and reevaluating the pieces of the data pipeline that change between iterations. A developer using it can explore a population of sessions, slice and dice by any of the signals derived about those sessions, and visualize interesting instances of behavior to converge on conclusions and strategies. Alright, so now that we know what TA is, what exactly do we mean by performance? Well, we could mean efficient code, or user responsiveness, or making the best use of resources, or scheduling operations in a smart way, or prioritizing important or user-facing actions over those that can wait or aren't user visible. Of course, performance means all of these things, and some of them seem fairly simple to address or make judgments about. But as your user population and the sophistication of your app increases, it can become quite difficult to make broad characterizations about performance or develop improvement strategies. Now, my wife is a clinical psychologist who also works in tech, so I like to pretend that I'm a technologist who also works in psychology. In psychology, there's something called Maslow's hierarchy of needs, which describes the layers of human need. Starting at the bottom with basic physiological needs like having shelter and enough to eat, moving up through having reasonable safety and security to psychological needs like love from friends and family and feeling appreciated or accomplished, and only then reaching what they call in pop psychology self-actualization, feeling fulfilled and having reached one's full potential. These are all real human needs, but the pyramid shape is supposed to illustrate that each layer of need can only be addressed if it's well supported by the layers below. Someone who's starving or homeless isn't going to pay much attention to or get much benefit from any interventions focused on improving their self-esteem. What they need is food and shelter. Now, Maslow did his work in the 40s, so this model may need a bit of updating for the modern world. But, you get the idea. So I'm going to use this model to kind of segment the market here with regard to performance analysis and focus our attention on the kinds of performance problems for which TA is most useful. Standing in for those basic physiological needs here at the base of our pyramid, we have basic efficiency and responsiveness. If I need to run a synchronous function that takes 2 seconds to execute on my target hardware before I can present any feedback to the user, well, I have few options aside from optimizing that function or deferring some of the work to a background thread. This is a basic need that most non-trivial app has to pay some attention to at some point. Once those basics are in place, though, further improvement usually require turning attention to issues around orchestration to share limited resources like RAM, I/O, and network bandwidth between different components, and adaptation of those strategies to different device types, network conditions, or even user profiles. And likewise, once we have systems in place in our app to do intelligent orchestration and to adapt that orchestration to various conditions, we can use this contextual reactivity to choose the best strategies and policies for any encountered scenario to make sure each experience a user has is a responsive and performant one. Now, the dominant factors at the bottom of the pyramid are generally synchronous and have easily determined causality and mitigation approaches, like optimizing a method or sending some process to an async worker. These types of problems are relatively simple, and there are many performance tools like traditional profilers that can be used to understand and take action on them. But as a product matures and you move up the hierarchy, things get more asynchronous and effects are more indirect. And improving performance is more about scheduling algorithms, caching strategies, and tiering different experiences for different device classes. These interventions require a more holistic understanding of the system, and using data analysis to obtain this understanding is far more challenging than drawing a flame chart or finding method hotspots. At the very top, we're asking our app to respond to transient fluctuations in network conditions or resource utilization with strategies that optimize performance under those conditions. This might involve trade-offs between competing concerns or tailoring surgical interventions for particular underserved cohorts while doing no harm to those who are already happy. This all increases the complexity of analysis and the variance of the behaviors we're trying to understand, and measuring whether our app made the optimal choices for any specific set of transient conditions it encountered during a session and providing enough detail about those circumstances to help with ideation about what could be done better requires sophisticated data analysis of a different flavor than most data systems are designed to support. Transient analysis is designed to help solve the types of problems we encounter as we climb to the upper tiers of this pyramid and look for a data-driven approach to guide our optimization strategies. So, it's these kinds of relatively complex performance analyses that one might use TA for. Getting visibility into the specific conditions that cause long-tail latency or other outlier scenarios, characterizing performance not with regard to some universal threshold or average, but with regard to specific observed conditions, understanding not just how fast did we get it done, but also how fast could we have gotten it done given those specific conditions. This understanding of what the ceiling is for a given scenario can also be used in strategic planning to do opportunity sizing to understand how much potential there is in a particular improvement approach before that work is prioritized. We've even used this capability to simulate what optimal strategies might look like and validate them before deployment. TA has also proven valuable for validating that teams are goaling on the right metrics and that the improvements they make to those metrics are really resulting in better experiences. Finally, when the point of diminishing returns is hit and goals are found to be in conflict with one another, for example, when lifting one team's metric inevitably ends up regressing other teams, TA can be a source of truth for understanding the trade-offs that are involved and giving the two teams real data and any negotiations they need to have. So I've got about 10 minutes for a demo. So I'm just going to try to give you a tour of the UI and a flavor of what the analysis workflow looks like. and leave a bit of time for questions at the end. We'll start out with a very basic, generic session visualization. This is the TA session visualization interface. Down below here, we can see a lot of available tabular views of event types. And then up here, we have a time-based visualization of these events. You've all seen visualizations like this. Events are localized at points in time, or for most of these events, spans of time. We try to allocate areas for different types of events and show them in several distinct swim lanes per event type. Now, in this example, we're going to be investigating the degree to which network congestion affects the perceived performance of image loading for the display of stories in the Facebook feed. You can see there's a lot of details available about each of these events, and some of these even mention images. I suppose it's possible that a very smart human could make sense of this very raw event data and come to some conclusions about congestion, but personally, I'm not one of them. In order to understand whether congestion is contributing to some particular performance problem and to what degree, you want to be able to understand these events in terms of the amount of data that's been requested by the client, but not yet received. So I'm going to bring up a higher level visualization of some of this networking related data, which we call a content type burndown. Now, a lot of what a data developer will be doing with TA is writing code to transform lower level events into a more abstract, higher level information dense representation of the session, which can then be visualized in terms of those higher level and often domain specific concepts. This is a stacked area graph. The vertical axis is the number of bytes outstanding that have been requested and not yet received. The color represents the type of content, images, video, Facebook GraphQL requests, and so on. With this visualization, we can get a sense for the amount of data that's been requested at any given time among all content types, and thus start to get a sense for what content types might be responsible for excessive network traffic and congestion. But we're still not there. In order to understand how much bandwidth is actually available for use by the app, and therefore to what degree delays in delivery might be due to network congestion versus other factors, we'd also like to understand the overall total bandwidth observed at any given time, and make a comparison with the effective bandwidth delivered for any given request. So atop this network burndown, we built an estimate of available bandwidth. And we can use this to compare the observed bandwidth for any given request to the overall delivered bandwidth and build a model of network contention. I'll add one last, even higher level visualization to the mix. Video is a domain that requires a lot of sophistication in how it deals with the network in order to deliver even a decent experience. As you can see, a lot of the bandwidth in this trace is being consumed by video, classified here into immediate chunks needed for immediate playback, those simply being buffered, and those that are being prefetched, as well as those that might have stalled. So here, we can see a high-level visualization of a video playback session derived from all this lower-level data we see above. Among various other pieces of information, which really will only make sense to someone who has some understanding of video performance and, someone who can take quick action to resolve a problem related to video, we see that we're able to assign root causes to stalls, which include congestion and CDN effects. Now, all this is great for understanding individual sessions, but the question is whether anything we see in this session in any way represents a common experience or one that is pervasive enough to focus on with your limited app performance improvement budget. A vital piece of the puzzle here is that all of the data we're using to draw these visualizations is also first-class data in our data model and can be easily aggregated and explored in an aggregate context. So now we're going to jump out to view this set of traces in aggregate using the signals derived by these domain modules. This is the TA aggregate UI, where we can explore and characterize aggregate behavior. On the left, we have what we call our filter tree, which lets us slice and dive into the data by any of our derived signals and compare different slices of data. On the right, we have cards that represent the aggregate properties of our selected attributes, in this case broken down into numerical fields, which we visualize as a continuous distribution, and categorical fields, which we visualize as histograms. The system automatically infers the best visualization for each field based on its data type. At the bottom, we have a sample of data rows from the selected filtered subset of data. So in this case, our query is generating one row for every HTTP transaction seen across the 300 or so traces in our sample dataset for a total of about 40,000 rows. I'll just go through a single iteration cycle here to demonstrate the workflow of a TA developer. So again, we're interested in whether congestion contributes to image loading performance problems. Based on the kind of pre-cooked data we just looked at some visualizations based on, it's fairly easy to determine whether a given HTTP transaction is competing for bandwidth with other requests. So to simplify congestion analysis at the aggregate level, our congestion domain module implements a Boolean signal here that we generate per transaction, which tells us whether a given transaction might have been slowed by congestion. We can use this signal in the aggregate UI to select only those transactions which were likely impacted by network congestion. Once we selected that subset, it shows up in our filter tree, and we can compare with the distribution of data over all transactions, or for transactions that occurred without the presence of congestion. Now, we're building atop some sophisticated analytics here, and I won't dwell on the details of how these judgments are made by the analytic code. Part of the point is that a data developer shouldn't need to know that. They can use what the library gives them, but can detect inconsistencies and go and fix bugs as they're found, just as they can in any other code. But among the components that have been built, we have here a classifier that tries to categorize the cause of the congestion. We can see here that for almost 24% of the transactions that we've designated as having been affected by congestion, we don't know why. The root cause of the current version of our domain module has selected is unknown. If we click here, we've now selected only those transactions which were likely congested, but we don't know why. Let's go below here and look at some actual examples of these transactions and see if anything jumps out of this. Now, it so happens that this trace we've already been looking at is one of these unknown congestion types. So let's take a look at it and see if we can figure out what's going on. So already, using the content type burndown, we can see there's an image request here that has to wait around for a long time before being fulfilled. While on the other hand, this bright green category is getting almost all the available bandwidth. The bright green we can see is prefetched video. In other words, video content we don't really need right away. So we've got a pretty obvious single case here where an image request is being delayed due to congestion caused by a large video prefetch. And it's likely we could have gotten that image on screen faster with better coordination and prioritization of these requests. So a TA developer focused on image performance might see a few examples of this behavior and naturally ask how common this scenario is at an aggregate level. Is this a useful vector for improvement? So to answer this question, we're going to write a little bit of code. We're going to switch windows over here to our IDE. I'm using IntelliJ. This is the analytic code being executed by the workbench to generate all these signals and attributes that are being aggregated. And right here is where we assign a reason for the congestion. You can see these two lines have been commented out that check for the existence of a large prefetch. When we uncomment them, the system's going to notice the code change, recompile the code, hot load it into our Spark session, reevaluate anything that may have changed. So we're back in the aggregate UI now, and we see the system has picked up our new large prefetch category. Just making a judgment on a transaction by transaction basis whether this request happened at the same time as a large prefetch was going on. We can see that the scenario happens in less than 3% of all transactions. But in those that show delays due to congestion, it's almost 5% of those. So at this point, we can go through and look at examples of this problematic behavior and confirm our classifier is working well down here. We can examine those examples for insights about what action we can take to change our scheduling rules. Or we can use this new signal to slice our data and compare with other aggregate characteristics of these groupings. I can use these signals along with our filter tree UI to select subsets of the data to compare with one another to see how the distributions of attributes differ between them. For example, if we know our request scheduler is already designed to avoid this kind of priority inversion, we might try to understand what other common factors all of these cases have, which might explain why our algorithm failed in these instances. So that's about all I have time for today. I'm going to wrap it up and stick around for any questions. Thanks a lot, everyone.
Thank you so much, George, for an amazing talk. Looks like we already have some questions, and one of them is probably very expected, whether it's open sourced. So any...
Yeah, not quite yet. I definitely think that I mean this has been a big ambitious project. I'm pretty eager to to get some as Tara said, it would be nice to have common infrastructure for all this. We've open sourced other parts of our tracing and analysis and collection solution. I think earlier you saw the black box talk that mentioned Profilo, which is the open source version of our internal Loom trace collection system. So I would like to see that. I don't, we're going to have to see. We have a little while to go as we sort of game out how to productionalize some of these things and make sure that we have all the workflows clear. But yeah, I'd love to get it open source eventually.
Awesome. Looks like we currently don't have any other questions, so I'm going to go ahead and ask my question. It looks like transient analysis actually heavily leverages something that I'm a huge fan of, which is the domain understanding. And I'm curious about your thoughts and challenges around getting enough domain understanding from people who are writing these transient analysis scripts.
Yeah, so this is a good question, because I think we're kind of going against what we see as kind of conventional wisdom in the sort of data engineering space right now. ML is kind of used as a really big hammer that's applied to a lot of things, and I think the conventional wisdom is that domain expertise is going to be automated away eventually, because we can just throw it into a lot of hardware and have it figure out what the important factors are and kind of pull out some kind of domain model. I think we take a different approach. We don't like that for a lot of these kinds of problems, because whatever you get out of ML, as nicely clustered as it might be, there's very little meaning there. And at the end, you're always left with someone to actually give it meaning. Humans, the only ones that can do that, right? And so, instead of aiming toward a world where I think a lot of times people use ML because domain expertise is seen as being so expensive. And I think the reason it's expensive, my feeling, at least partially, the reason why it's so expensive is because we throw it away every time we build it. We build a query that's written in SQL and goes into some data warehouse, ETL pipeline, and then how does that thing work? And the domain experts don't use SQL, and so they can't look at it and edit it, and so we have to rebuild it all the time. And if we did this in software, then software would be intractable in terms of domain experience as well. On Android, I can take a video library and that someone else wrote, and I don't have to understand video, and I can tell it to play some video, and look, I'm a video expert now. Well, you can't do that with analysis software right now. You don't really have good ways of encapsulating analysis domain expertise that can understand a series of events and tell you what actually happened in any kind of terms that you can understand at a high level. And I think that's kind of one of the big challenges that we're going after with this project, is to try to make it so you can encapsulate these things, give you ways of encapsulating these things in software, just as we can encapsulate functional libraries.
Awesome. Thank you, George. And Matt has a question. So, wow, that hot reloading is pretty impressive. How much data needs to be reprocessed, and how expensive is it to do?
So in this version of the system, it's a good question too. This kind of responsiveness is really important to our workflow. What we found is that first, we have to work with far fewer samples than you have to if you're looking at everything in aggregate, right? Because you have fine-grained examples of everything, and you can, you get a lot of examples. Like for those 300 traces, we had 40,000 transactions. There's a lot of different conditions that are covered in that. So I think the first answer is, in a lot of cases, you don't need as many samples as you would if you're just looking at aggregate analysis. But of course, yes, you need to be able to scale up. What we do today, we have kind of it's kind of a two-stage pipeline that kind of does all your joins, does the heavy lifting, and then we have kind of an extraction that takes it from this big hierarchical data model into what we call projections that are just rows that can be easily aggregated. In general, all we're hot loading is that projector right now, and so we have a lot of pre-calculated results for the big set of data, and then we kind of run a much faster sort of extraction that can still run arbitrary code, but it's working with it's only at the end of the tail end. So you don't have to recalculate the whole thing. We're working on a new version of the system that will do a sort of a diff between the pipelines that you give it. So as you change the pipeline, as you change the analysis logic, it'll actually intelligently figure out what has changed and recompute that and learn cache points and things like that. So that's a big focus of some of the work that we're doing right now, is to make sure that we can maintain that kind of hot reloading. It's going to be kind of a little bit React-like, kind of comparing this pipeline to that pipeline, seeing what the differences are, computing cache points, and then being able to swap out only the components that need to.
Thank you so much, George. Yeah, that's amazing. I'm very much looking forward to see the progress on this, and maybe you'll agree to join us for the next event and present some new exciting findings that you get.